In this video, I want to find a volume of a region using both the shell method and the washer method, just to give us one more chance to compare the two. This example comes from our calculus book, Thomas's Calculus in its 14th edition. In the problem, the author explains to us that for some regions, both the shell and washer methods work well. Now, in other cases, it might be beneficial to pick one over the other. The goal in this problem is to do it two different ways and get the same volume both times. Now, your author here is actually asking us to do this 4 different problems to revolve this region around both coordinate axes. In this video, I'm only going to consider the y-axis. So, we'll find the volume of the region generated by revolving y equals x and y equals x squared, the region contained by those, around only the y-axis. We're going to use the shell method and then we'll use the washer method. So let's go ahead and sketch the region. Y equals x, not a very interesting line to graph, and then y equals x squared. So we get this little bit of a sliver between the line and the parabola. And we're going to be revolving it around the y-axis. So we're asked first to use the shell method. And so I'm revolving around a vertical axis, so I'll have vertical shells. So there's the rectangle I want to imagine revolving around, and drawing this region very small. So you know what, I think I'm gonna take another stab at it and just increase the scale a little bit, make it a little bit easier to deal with. Exaggerate the parabola a little bit. And there's that rectangle I'm thinking about. So for the shell method here in part A, I'll be integrating 2 pi times a shell radius times a shell height, and I'll be revolving around the vertical axis, so I'll be integrating with respect to x. Well, my x's start at 0 and stop at 1, so there are my bounds. I'm revolving around the y-axis, so the shell radius is just an x value, and the shell height is a difference between the two functions. So not too challenging of a definite integral to evaluate. All right, so we just need to evaluate from 0 to 1. All right, so we have 2 pi and then 1/3 minus 1/4. So let's see here. Thinking out loud, that's going to be 4 over 12 minus 3 over 12 is 1/12. So I have 2 pi over 12, or 1 pi over 6. And so there's the volume of the solid generated by revolving this region around the y-axis using the shell method. All right, part B, find the same volume using the washer method. And if everything works out, we should get the same volume. If we don't get the same volume, we've either broken math or we've done something wrong. All right, so still revolving that region around the y-axis, this time thinking about shells. Thinking about washers. So I'll have a big radius minus a small radius. Now, I'm revolving around the vertical axis with shells. If I think about the radius, the big radius and the little radius, these are going to be functions on the variable y. So I need to find those equations. Well, let's see. The small radius, well, that would be x equals y, right? Because that was the line y equals x. So when I solve it the other way, I just get x equals y. Nothing very interesting there. And then the large radius goes all the way out to my parabola. So let's see, that would be y equals x squared. Solve for x is x equals root y. All right, big radius squared minus the little radius squared. Oh, and the y values, I'm also integrating on the y-axis from 0 to 1. All right, let's see what happens. All right, here's the moment of truth. I end up with 1/2 minus 1/3 times pi, and that's a 3/6 minus 2/6 is 1/6, or pi 6. And that's the same volume we got last time. So we've been able to do this one 2 different ways and get the same volume both times.